Good day, guys, and welcome to the seventh session, part one of the Diverse Node Mobility Front End Development Program. Today, we will discuss the Module 8. Right, so guys, I'm going to share my screen to you. Okay, here. So in this module, you will learn about the preprocessor, hash include how to make use of the header line, hash define, simple and parameterized macros, and the hash undef directive, and also predefined uh, processor symbols, marker operators hash and double hash, conditional compilation, the hash if and the hash if def directives, and also avoiding multiple compilation of the same header files, scopes of declaration, storage and classes, user-defined types, pointers to functions, and also lastly, analyzing and creating complex direction. So let's have our next slide. Alright, so here we are going to define the role of preprocessing. We have mentioned the preprocessor many times since the first lesson, and we have used the hash include directive very often too. Now we are going to tell you more about the preprocessor itself and its directives. There is more than one. You already know that the preprocessor is responsible for the initializing process of the program. This process occurs before the compiler starts to analyze the source code. Thus, we can imagine that the position occupied by the preprocessor in the overall structure of the C language compiler is very important. As you know, the effects of the preprocessing are visible only to the compiler. The form of your program, when it leaves the preprocessor, it disappears at the same time the compiler exits. This time that the preprocessed source code is not stored in any way. Fortunately, compiler developers know well enough that you may something need to know what the code looks like after it passes through the preprocessor. That need occurs when something strange happens, and you suspect that it may have been caused by some incorrect use of the preprocessor directives. So here's the illustration of the preprocessing. So for example, here's the compiler, and we have our source code, and after running the source code, the compiler will surely check the preprocessor, and after that it will generalize or analyze, or will run or give you the output for the function that you have declared inside after the preprocessor, which is the header files, and then the binary code, which is it will restore the binary code and give us an output to the console. If you are familiar with working on an operating system console, you can perform a simple experiment. Let us assume that you use the GCC compiler infrastructure, and the GCC compiler may be launched directly from the command line. If if you want to know what your source code looks like after preprocessing, you will need to use the E option, for example, like this: GCC dash E, then program, then the name of your program, and then its file extension, which is .c. Okay, so assuming that your source code is located in the prog.c file, this option causes the compiler to stop as soon as the preprocessor completes its function. The compiler doesn't validate the program, nor does it translate it. Instead, the preprocessor source code will be sent to the standard output, and all modifications made by the preprocessor will be marked in a specific way. If you want to preserve the preprocessed data, the text, for further analysis, you can redirect the standard output to a file and view it in your favorite text editor. You do this in the following way: GCC, then this would be the code, GCC, then dash E program C the file name and the file extension, which is .c, and then greater than symbol, and then output file name. Right, so you can freely choose the name of the output file, but ensure that the output file name is not the name of your source file or any other file you want to keep, because you may lose it forever. Note that the preprocessor inserts various information into the code. The markings are ignored during the verification and translation of the program. You will recognize them by the hash characters in the lines, just like in the preprocessor directives. We encourage you to use the dash E option as often as possible during our current lesson, because it will be very instructive and very useful. Let us start with some general principle. The preprocessor directives always begin with a hash, which must be first visible character in the line. Second, if the preprocessor directive doesn't fit one line and needs to be split up, or to be split, you must put the backslash character in the place where the directive is broken. Just like for here, the example would be hash include stdio.h. We are going to put backslash after the hash include uh, to place when the directive is broken. And third, any preprocessor directive placed in a particular file acts only inside this file and nowhere else. Now let us discuss the preprocessor directives and its operators. Okay, so including a file. The hash include directive works as follows. First, the preprocessor looks for a file named file name. But if you enclose the name inside quotes, it searches for that file in the same directory as the file containing the directive. Otherwise, it searches for the file in the compiler's default directory. Unix system will usually use backslash user then backslash include for this purpose. Next, if the file is not found, the preprocessor reports an error. Otherwise, the hash include directive is replaced with the content of the included file. Third, the included file may contain an hash include directive too. In addition, a particular compiler may impose a certain limit on the number of nested inclusions. And lastly, you may use the hash include directive in any part of the source file, not only at the beginning. All right. So we can also use the header file in any part of the source file, not only in the beginning. So let us assume that we have two source files. The first one is named source1.c and contains the following text. Int main void, then we have hash include source2.c. The second one is named source2.c and looks like this. Int I is equals to 0 and then return I. When you start the GCC compiler with the following program, gcc hash e source1.c, you see the following text on the screen. So this would be the output of that. Okay, so here source1.c, then empty spaces here, then source1 int main void. Then inside the block, we have the source code of source2, which is int1 is equals to 0 and return to I. So as the lines marked with the hash character, as used internally by the compiler, we can ignore them and assume that the final form of the preprocessed code looks as follows. So int main void, then inside it would be int I is equals to 0, return I. And then you should do some experiment for yourself with nested include directives. So the process or the output for this code will be this, but you can ignore those hashes and other characters. And as a C language programmer, you can see those code as this one. Okay, so ignore those hashes because it is just part of the command line. All right, so next, let's have our next slide. All right, so three forms of the directives. The hash-defined directive may take one of the following three forms shown in the editor. Let us explain first form of the directive now. Its operation is as follows. So the preprocessor, remember the identifier and text associated with it. So here, so the preprocessor remembers the identifier and the text associated with it. Next one, from this moment on, the preprocessor analyzes the source code, replacing any occurrence of the identifier with associated text. And lastly, the directive itself won't show, won't appear in the preprocessed source code. So that is the three forms of directives. So usually we use the third one. So let's have hash defined simple substitution. Here are a few examples. The source file is as follows. Look at the part of the code in the editor. Note pi is the identifier, while 3.1415 is a text. The preprocessed code will take the following form, second part of the code in the editor. So as you can see, the instance of pi identifier has been replaced by the text associated with the hash defined directive. The identifier used inside a hash defined directive, such as pi, is often called a macro, and the process of replacing it with corresponding text is called macro substitution. You usually write the macro names in the capital letters, allowing them to be distinguished from ordinary variable names. This is not an absolute rule, but fairly widely recognized in use. So all we need to do is remember that we are going to use uppercase or capital letters in creating macronames. So, and having the value is what we call macro substitution. This form of the directive is often used to improve program readability and to make it easier to modify. Consider the example in the editor. This program is not very useful in general, but quite handy for our discussion. Imagine that you have to modify the program so that it can deal with an array containing not just 100 but 5,000 in values. In how many places would you have to change the source code? Are you sure you wouldn't miss any? These modifications are often the reason for troublesome and persistent errors, which can be time consuming and extremely tricky. So we can extend the containing array in this example. So let's have the next slide. Alright, so let us assume that the author of the program has used the hash defined directive and has written the code in the editor. Changing the size of the array from 100 to 5,000 is now a piece of cake. All we need to do is replace the line define size 100 to define 5,000. So here we're going to make it 5,000. Okay, with the line hash defined size 5,000, recompile the program. Nothing else needs to be done. Pretty convenient, elegant, and safe, right? So that is how we change that 100 to 5,000. And we don't need to add the value itself in the array. All we need to do is write the name of the in the header file, just like size, right? So that is how we do that. Hash define disadvantages and perils. However, we have to warn you that the reckless use of macros can get you into real trouble. Your program may behave strangely and be completely intelligible. Let us take a look at the snippet. So here we have defined size 4 plus 4, int main, and then the function main. At a first glance, it would seem that the value assigned to the I variable is 16, actually 2 times 8. Unfortunately, nothing could be further from the truth. Don't forget that the preprocessor doesn't use the value of the identifier, but only replaces it with the associated text. A macro substitution will lead the following form in the preprocessed source code. So we have I is equals to 2 times 4 plus 4. So the I variable will be assigned a value of 12. So how do we get the 12? Because since multiplication having the higher priority, so 2 times 4 is equals to 8, then plus 4, so we will get 12 instead of 16. So how do we avoid such surprises? Well, you can use a pair of surrounding parentheses which removes any ambiguity. A proper written hash define should look like this. So we will add parentheses here, and we will enclose it the 4 plus 4 in a parenthesis. Okay, so the previous problematic source line will be preprocessed in the following way. So I 2 times 4 plus 4, sure, we surely won't cause any problem. All right, so let's have hash defined predefined identifiers. Many of the identifiers we have used so far are actually macros. If we take a look in the stdio.h and stdlib.h header files, we find the following hash defined directives. So we have define null, void, and here define eof -1, define seek underscore set, seek underscore current, and seek underscore ending. So that is included in stdio and stdlib.h. All right, so let's have the second form of the hash defined directive. Now we are going to focus our attention on the second variant of the hash defined directive. Its syntax is here. So hash defined an identifier, then the parameter list is enclosed with parentheses, and then after that would be the text. So the parameter underscore list element should consist of different pairwise identifiers and separated by commas. Note that the opening parenthesis should be glued to the identifier. No character is allowed between the identifier and the parenthesis. Otherwise, the preprocessor will recognize it as the first variant of the hash defined directive. A macro defined in this way is called a macro with parameters or a parameterized macro. When the preprocessor meets an identifier identical to the one defined as a macro and there is a parameter list after it, it takes the following actions. So first, each macro parameter in the text is replaced by the argument specified in the source code. The macro identifier along with the parameters list is replaced by the text composed of the first step. And third, the directive itself won't appear in the preprocessed source code. Oh, how about the parameterizing the hash defined directive? Okay, so let's analyze a simple example and consider the source code in the editor. So the first step of the macro substitution will cause the x parameter to be replaced with the macro argument length. For example, length. The following string will be composed length times length. So the second step will be replace the macro with a second composed string. Check the preprocessor source code in the editor. So that is how we do that. First, we have to substitute and cause the square x parameter to be replaced with the macro argument, which is this one. Okay, a macro is not a function. Note that a macro is not a function. It only looks like one. There are two very important differences between them which disqualify this comparison. Let us elaborate. Okay, so imagine that our parameterized a macro is used as follows. So first fragment of the code in the editor. So the square is a function. Then there's nothing remarkable here. The expression length plus 1 here is squared and its value is returned as a result. The SQR is a macro. Actually, don't be surprised by the process form of our source code. It will look like the second fragment of the code in the editor. This expression has little to do with squaring anything. Of course, we can avoid these unwanted effects by using the parentheses properly. If we rewrite the macro in the following way, just like this one, we have another x here and enclosed with parentheses, and then the separate x here will be enclosed with another parenthesis. It is work as expected. So if you are going to substitute that, so if f is equals to length plus 1 plus times length plus 1, and then it will add another parenthesis inside this one. So after this, if it is enclosed with another parenthesis, then it will probably give us the right answer, right? Because it will not be a commutative, right? So let's have another slide here. So let's analyze another example. Let us take a look at the snippet in the editor. The SQR is a function. It returns the value of length times length, and then the length variable is increased by 1. Since SQR is a macro, the f variable field will be assigned with the value of the following expression here. So this also means that the length variable will not be increased by 1, but by 2. All right, so let us take a look. So this is just a differentiation of the SQR if it is a function, and since SQR is a macro. So since SQR is a macro, then the f variable here is equivalent to SQR, and f is equivalent to length. So this one would be replaced or substitute by this one. So here, and let us check that this also means that the length variable will be increased by 1 but by 2. So as you can see, why it becomes 2 is we add another parenthesis here that will increase itself, or will the increment will apply to each length. Some examples of parameterized macro. Now take a look at the source program in the editor. The max macro here is designed to find the larger of the two numbers. Can you explain what will happen if there are no parentheses in the macro? We have provided the processed code in the editor. This is actually what we expected. So here, we are going to explain if there is no parenthesis. Of course, if there's no parenthesis here, we cannot, if there's no parenthesis here, we cannot identify what will be the first, or since there are priority table, we will get use of them, and we will use the proper symbols or proper operators that we are going to use for us to arrange or systematically or orderly arrange the operators for this formula, or for this type, or for that expression. Okay, so let's have the next slide here. With the max macro, we are able to write a more complex macro. Example is max3, which searches for the largest of the three values. It could look like the one in the editor. We agree it looks weird, but the processed text will look much weirder. So as you can see here in the hash defined tree, so we have the three variables, which is x, y, z here, and this is a formula that the max3 will, or the expression that max3 will be used to find the largest value of the three values um, that is written in the main function, which is a, b, and c. Okay, the third variant of the hash define directive. The third and syntactical simplest version of the hash define directive is as follows. Hash define the identifier. The directive affects preprocessor operations in the following way. It causes the preprocessor to assume that the identifier is a defined identifier. The directive itself won't appear in the preprocessed source code. And third, the source code is not changed in any way. So the preprocessor provides some features which can be used to check whether an identifier is defined or not. This may determine whether a part of the source code is to be compiled or omitted. This mechanism is known as conditional compilation. We will discuss it more soon. The undef directive. The undef directive cancels the effect of the selected hash defined directive and takes the following form. Hash undef identifier. The identifier doesn't need to have been previously defined. From the moment the hash undef directive is used, the identifier is not defined. So from the word itself, undef. Okay, so if we will add identifier, it will not be used or will not be defined. Okay, so let's analyze the source code in the editor. It is a bit complicated, so study every piece of it. Before the preprocessor sees the first hash defined directive, add is undefined from the preprocessor's perspective. So the appearance of the phrase would be I is equals to add, and then we have the parameter I. Is treated as a function invocation and doesn't elicit any reaction from the preprocessor. The moment add is defined as a parameterized macro, since it is defined here. Okay, so this is the macro. The second appearance of the line coded above will be interpreted not as a function invocation, but as a macro, because the preprocessor works before the compiler. Okay, so here, this is a macro, not a function. So the hash undef directive recovers the previous meaning of the add identifier. The preprocessed source code will look as follows. So here in this another directive, the undef directive recovers the previous meaning of the add identifier. So that would be our example. So that is how hash undef is used, or on how to use it. Okay, so let's have the underscore line underscore identifier. You already know that the hash define directive may be used to define your own identifiers. And you also know how these definitions can be cancelled by using undef, undef, right? A number of these identifiers are defined by the preprocessor itself. You can freely use these symbols in your program, but you are not allowed to undefine them. We are going to review the most important of them and show you some examples of their use. The first one is underscore line underscore identifier. So note that the double underscores enclosing its name, it's a general naming convention of the identifier declared it's implicit. So note that this is a double underscore, right? So wherever you use underscore line underscore, it is replaced by an integer literal equal to the line number where the symbol appears. This means that the symbol will have a different value in every line of your source code. Look at the code in the editor. Note that empty line intentionally placed inside the text. This code, when passed through the processor, will take the following form. So since we are using underscore underscore line, and we have already read that underscore underscore line underscore will give a different value in every line of the source code, which is like this. Okay, so we have 4, 6, 10. So the code compile and run will emit the following text to the standard output, which is this one. So we can use this symbol inside errors message to clearly inform that the user or the developer where the error encountered and diagnosed. Okay, your question would be how we get those numbers 4, 6, 10. So as you can see, it is equivalent to the line that they are written. So just like this one, this is line number, then underscore. So this is 1, 2, 3, 4. So this is 4, then this is 6, and this is 8. So we are going to add 10. So if you like to add 4, 5, 6, 7, 8, 9, 10, you can um here you can add another a printf here until, so it will probably give us the result 4, 5, 6, 7, 8, and to 10. So here, so that is how underscore underscore line works. How about the underscore underscore file underscore identifier? The file, the underscore file underscore file underscore identifier is always replaced by a string literal containing the name of the source file in which the identifier was used. Note that the string will be enclosed inside double quotes, like any other string literal in C language. This means that the symbol will have a different value in each source file. Look at the editor in the code in the editor. So here we are going to enclose the strings inside the double quotes. Just add after that as an argument this underscore underscore file underscore. Assuming that the code was placed in a file name file sim.c, it will take the following form after it passes through the processor. So here we are going to Okay, so that file would be replaced by the name, but by the file name itself. The same code compiled and run will emit the following text standard output. Okay, so output from the source file name filesim.c, which is the name of the file. So at this point, you might be a bit surprised by the syntax source code. So hello from the source file names is filesim.c. There is a rule in the C language that says that the string literal can be broken at any point with the character, and then any number of white characters may appear, after which the literal may be resumed with another character. This is exactly what we have done in the example. Consequently, the two literals above are equivalent in the following. So we have hello from the source file name file sim.c. Moreover, a source code written like this, int main void. Then we have this one. Okay, so return to will be processed like this. So here, and giving the same result above. So remember, guys, that if you are going to run this one, because we are using online IDE, so we don't save this file because this is just an online IDE. You can use IDE or other IDE to save your file and to identify which file name is written on your code. This but from this time, um we have main.c because this online IDE by default name the compiler or the code in the editor or the file named as .c, so we cannot get those this file name. Okay, how about the underscore date underscore identifier? The underscore date identifier is always replaced by a string literal containing text denoting the day the source file was compiled. The string is enclosed inside the double quotes, like any other string literal in the C language. This means that the symbol has a different value every day. Look at the code in the editor. So this code, after passing through the preprocessor, may looks as follows. So okay, here looks as follows and replaced by date. So this date string always contains 11 characters. That means that this code, when compiled and run, will emit the following text to the standard output. We are going to run this code and here. So this code, the date underscore will run your current date, right? How about underscore time identifier? Of course, this is all about time. The underscore time underscore identifier is always replaced by a string literal containing text denoting time, hours, minutes, seconds. The source file was compiled, and the string will be enclosed inside double quotes. This means that the symbol has a different value every time it is compiled. Look at the code in the editor. This code, after passing through the preprocessor, may look as follows. I was compiled at, okay, so 12/13/23. The time string always contains 8 characters. At this code, when compiled and run, will emit the following text to the standard output. So here it is the expected output. Okay, so I was compiled 10/03 and 5/54. How about the underscore stdc identifier? The underscore stdc underscore identifier, as in standard C, is defined if and only if the following statement is true. The compiler is operating in compliance with an ANSI C standard. When ANSI mode is on, it means that the compiler honors any language elements described in the standard documents and no extensions or limitations are applied. If the compiler is not working in ANSI mode, the symbol is not defined. So all we need to do that is make sure that the compiler is working in ANSI mode. For us, the symbol will be defined. How about the hash operator? The preprocessor recognizes the interprets only two operators. They are used to facilitate string manipulations performed during macro expansion. It's important to remember that these operators act only during the preprocessing phase and disappear from the source code when the preprocessor completes its work. Do not try to use them outside of the hash-defined directives. The hash operator is a prefix unary operator which is used in the way we have shown here, hash argument. When the argument is a string, where the argument is a string, usually retrieved from the macro parameter. The operator affects the macro during the expansion phase and causes its argument to be enclosed in a pair of quotes, thus transforming the initial argument into the following form. So we have um, double quotes and the argument. Note that you can't do this in any other way because a macro is similar to the following. So define then quote x and then double quote and then x will not work as expected. The preprocessor doesn't look inside the string literals. They are untouchable to the processor and therefore the X symbol is not recognized as a formal macro parameter. Here's the solution. Define quote X and then hash X. This macro when used in the program in the following way. Quote and then Mary had a little lamb will be expanded to the form Mary had a little lamb. So remember that don't use double quotes. Instead of using that, use hash. We want to illustrate the purpose of this operator by showing you a practical and useful example. Imagine that you are developing a complex program. You want to have a handy simple mechanism that allows you to display the values of key variables. You definitely don't want to write a snippets like this. Variable a print var I is equals to I, then variable total ship. Writing the snippets makes every developer wary and nervous. And what's special annoying? What is especially annoying is that you have to write the same phrase, the name of the variable that you need to display twice inside a formal string and once again as printf's parameter. A godsend may come in the form of cleverly constructed macro using hash operator. Take a look at this. Define and then snap hash snap then x print f variable then hash x is equals to percent d then block slash n then x. So instead of writing again and again um this lines, you can write it on your define or in the header file. So we will use it snap pictures of a variable, not literally, of course. So snap. Reminder that we will have a snap. Right. So we are using new macro in the code editor. This code will be expanded to the following form. So if we are going to take a look at this, so the compiler will read it just like this. So take a look here. So instead of writing these long lines, you can just add or call the function snap or the macro snap. Macro snap. So this is I. Take a look at that variable hash x. So instead of writing the variable here, we use hash x. Okay, and then all right. So that would be the printf, then variable, then another one, which is take a look at this I, counter, and ship total are all variable. So instead of calling the variable, you are going to use hash x. Okay, that stands for the variable that will be called later. Okay, so this is how it is called: I, counter, ship total. Okay, so study carefully how the snap macro is expanded. It will give you a complete picture of the possibility offered by the hash operator. We suggest that you compile and run program for yourself. Okay, so if you are going to run this one, of course, we are going to have the same result just like we did earlier. We are going to run this program. Okay, so that would be the same, but it is convenient, this one, and it is time not time consuming. How about the hash operator? The hash operator is a binary operator requiring two arguments and is used in the following way: argument 1, then hash hash, then argument 2. Note that you can do this in any other way because a macro similar to the following: hash defined, then glue, then xy is enclosed with parentheses, and then xy will not work. The preprocessor recognizes the xy identifier, not x and y. Here's the solution: hash defined, then glue, then x, then y, then hash, and then x, then hash hash y. A glue macro used in the following way: glue Mary had, then comma, a little lamp, will be expanded to the form Mary had a little lamp. Alright, so let's have the hash if, hash and if, hash else, and hash l if directives. Generally, conditional compilation directives are used in the way we have shown in the editor. Okay, so let's check the code in the editor. So we have the hash if, and we have the expression 0, and then after that will be the text 0. How about elif will be expression 1, then text 1, elif expression 2, and then text 2, and then so on. Then another elif will be expression and then it's text and then else, hash else, and then text e. So this is how we use them. So if we are going to use this directive, so first all we need to do is uh, start with hash if, and then if you are having so many conditional statement, then use l if, and then if it is on the last part, then use else, and if you're going to end the conditional statement, use end if. So if you use the hash if directory, you're obliged to use the end if directive too. Between these two directives, any number of hash elif directives and at most one hash else directive may be used. The expressions placed after the hash if and hash elif are used to decide which of the text will be passed for further compilation. Because the expressions are evaluated by the preprocessor, not the compiler, they must, at the moment when the variables values are not yet known, be evaluated exclusively by means of. Okay, so here's a few items. First, preprocessor symbols that are assigned numeric values using hash defined directives. Second, operators, plus, minus, multiplication, then this is slash, then double, this is arrow, two kinds of arrow, and then greater than, and greater than, less than, greater than or less than equal, then equal, not equal, modulus, and and or that.
Okay, so sub expressions enclosed in parentheses. Next, a pseudo function named define, whose argument is a symbol and whose result is 1. If the symbol is defined, otherwise its result will be 0. Some of the directives may be simplified, for example, hash if define identity can always written as if def ident, and a directive like this, if not defined, then enclose it with parentheses ident, may take the form if and def ident. The process of interpreting this directive is as follows. First, the value of the expression 0 is evaluated first, and it, if its result is a non-zero, text 0 is passed to the compiler. In this case, all other the texts are ignored and won't be compiled. Next, otherwise, the preprocessor calculates the value of expression 1. If non-zero, it causes text 1 to be compiled and all other text to be ignored. And lastly, when none of the expression are evaluated and a non-zero value, only the text associated with the hash else directive will be compiled. Right, so let us look at the two simple examples illustrating how these directives could be used in your programs. Imagine that due to some unexpected issues, you decide to use the snap macro in your own code. The macro helps you to identify some mistakes and to locate the very first reason to unexpected program behaviors. Your program seems to be working properly right now, while your code looks as follows. Int elements so to sort, and then equals read elements from file, and then snap elements to short. Of course, you can remove all the sources line, which refers to snap, but okay, you might think we sound a bit paranoid, but what happens if the trouble returns? You can exclude the possibility that there are some other errors in your code and that you will have to look for them once again. By the way, the process of searching for errors and removing them referred to as debugging. It's an old joke that developers don't make errors at all. The errors are caused by bugs living inside the computer. So you have to debug your code when you suspect that it doesn't work as it should. Is it possible to have Snap working when you're debugging the code and to turn it off when debugging is completed? Yes, it is. You can use the conditional compilation directives for that purpose. Take a look at the editor, the code in the editor. So the line referring to the snap will be compiled when and only when the debug identifier is defined, and it will be uh, ignored otherwise. There are two ways to define the debug identifier. You already know the first way. You have to add a line like the one below somewhere in your code, but before the first hash if directive, of course. Hash define debug here. So it will be placed in your hash before the hash if directive. The second way is based on the fact that all C language compilers are able to define an identifier outside the source code. You can order the compiler to define any identifier before it starts to compile the source files. Refer to your compiler documentation for details. The GCC compiler needs an option to do this, and it looks as follows. The GCC and then um, dash d debug file c dot c. The source file name file c dot c will be compiled, assuming that debug symbol is already defined. So that is how we call or run or put it on our command line to run the file name, the file itself with debug. Take note that this is an uppercase, all caps. So avoiding multiplied compilations. It's often the case that a header file is implicitly included more than once. In one source file, we can imagine the following sample configurations. Defs.h to functions.h to functions.c, defs.h to function.h to main c, and then defs.h to main c. The header file name defs.h defines some entities used by all other files. Next, the header file name function.h contains the prototype of several useful functions. The file includes the defs.h file. And then the source file named function.c contains declaration for the above functions. The file includes the functions.h file. And the source file name main.c contains the main function which invoke the functions declared in the function c source file by including its header. In addition, main.c includes the defs.h file. Assuming that the arrow symbol in the is the equivalent of the phrase is included by, we can draw a scheme you can see in the editor. This means that when we compile the mains.c source file, we cause the defs.h header file to be included twice. Firstly, by the functions.h header file, and secondly, by the main.c file. This situation is highly undesirable because some of the identifiers cannot be defined or declared more than once. Conditional compilation directives may be nested like ordinary conditional instructions. Let us analyze the source code in the editor. Compiling this program will result in an executable code which emits the following text to the stdout stream. Okay, so we will have the output, the array is not so large, and then when the size is defined with a value less than 1000, and this text, the array is very large. Appears if size has greater than 10,000, the text array will appear otherwise. Okay, so since we have a size and its value is 100, if we are going to run this program, probably it will give us the array is not so large. Okay, so since we have a conditional statement here that if size is greater than 10,000, then it will give us the array is large. Okay, right, so let's have the next slide. We are going to show you a sample content of our files now. Carefully analyze all the inclusions taking place when the main.c file is being compiled. Okay, so take a look at this editor. Okay, so here, so this file name is main.c. How do we prevent the deps.h header from being included more than once? We can do it by using the conditional compilation directives. Every header should use the following trick. First, check if a special individual identifier is already defined and ignore the rest of the file if it's true. Otherwise, define this symbol. It's widely accepted that this special symbol is derived from the header file's name in this simple way. File name, header.h, and then identifier, underscore header, underscore h, underscore. Now we can slightly modify each of our headers. Analyze the modified code. Now can you explain the depths that each header file is compiled only once? Okay, take a look at it. So here, depths.h was used by, we use hash if and def here. So it is only compiled once. Why? Because at first, we just only declared it or call it, and then it was defined, and then after that, it was end by hash and if. All right. Okay, so here we have a lab, and objective of here is of this is familiarize the preprocessor disjoint compilation, header files printing on screen, and the scenario would be, do you remember lab 6.1.8.11? Take the sources from that lab and modify them, add hash define and hash if and def in the header files, triangles that h to avoid multiplied compilations. Okay, just wait for a minute, guys. I will get the source code in that lab. Add a macro to log information to the screen. Call this macro before each function call and pass the name of the function into the macro. The macro should get the line and file name from the other macros. Your version of your program must print the same result as expected output 5. So here we have, okay, so that talks about two kinds of triangles, right? The regular triangle and the second triangle.
Alright guys, so I'm going to use a sample solution here. So here, so since it is using or calling other files here, we are going to delete this one, and instead of that, let us paste the triangle H. So here, let's cut this and paste here, and then let us delete this one because this is for a separate file. Since we are using one file here, just delete it for now, and also here. All right, so we are also going to delete no login info because we are not using or calling another separate file here. So if we are going to run this program, let us encode 5. Okay, so we will get those two kinds of triangle. Right, so another laboratory activity. So the objective of this activity is to familiarize you with a preprocessor, printing on screen function calls with parameters, calling function with parameters, function return values, and printing on screen. So the scenario is to write a function that checks whether or not a given string is a valid IP address. In human readable form, of course, this function should return 1 if the address is valid and 0 if not. Your function should check if three things. There are 4 parts in the string separated by dots. Next, each part contains only digits and each number is in the range of 0 to 255. So for converting string fragment into integer values, you can use the strtol or atoy or scanf functions. So separate the declaration of the function from its full definition and write the second function that calls the first one and then prints an appropriate message. 127.0.0.0.1 is a valid IP address, or A.B.C.D is not a valid IP address. Write a code to test it with values called function. Second function, do not limit yourself only to those values that we have given to you. We did a similar task in 6.1.6.9. The only difference that between this lab and the one is that here you need to define all the contrast constant with the preprocessor defines. So we are going to use stdlib.h here. So you should also give them an appropriate name. After the whole process, you can judge which option is better, to change all the possible constant or leave some of them is in their natural form. So here's the expected output. Okay, so we are going to add another two headers here, and this would be include string that h, and then include std library or standard library that h, and then before Before adding a code into the main function, we are going to declare the pointer here. I'm going to say it is check IP. And then we have a character. Then, right, so next would be another function, and I will name it IP valid and the pointer. Right, so inside our code, main function code, I'm going to print this expected output, and later um, we are going to judge them or to process them. Print IP valid 127.0.0, then a 1. Right, so we have 1, 2, 3, 4, 5, 6. So we have 6, 2, 3, 4, 5, 6. Good. Okay, so there are a lot of cases for the error. Check our code. Okay, so here, fifth, and then sixth. All right, so we already have the sixth. All we need to do is add the hash define. Since it is included in the standard library, let us first use define part underscore size 5. Oh, sorry. Okay, next would be hash define start digit 0. So take note that all of this are unreserved keyword by standard library. Define stop digit by 9. Then hash define dot character. Define maximum digits for, and define minimum digits 1. And lastly, we have define still. So all of these are macros. Acad good parts count. And let's have three. All right, so I just copy and paste the previous laboratory on 6.1.6.9 after the define on the directives. After that, I just copy all of the other function except the main function here, and just replaced all of the arguments here, part size and the start digit and the stop digit. I just replace all of their variable, and I based on the macros that I've declared on the directives. Okay, so if we are going to run this program, we will get the same result as it was expected. So the scope and what it really is. By declaring a certain identifier in the C language program, you not only create a new entity, but you also define where the entity is accessible. Consider the example code we have provided in the editor. This is a complete source file. Just looking at it, we can say first the variable identifier is accessible to the whole file, source file. You can make use of it inside any function. Then the X is identifier inaccessible only within the fun1 function. Fun2 knows nothing about it, and it is not allowed to use it. In the same conclusion applies to the I identifier, and fun1 and fun2 are accessible to the whole module. Okay, so the scope of the declaration is a part of the program in which a particular identifier is recognized and accessible. Additionally, you can add a linkage type to the declaration. Linkage is the process of deciding if an identifier that has been declared more than once refers to the same object. There are three types of linkage. First, internal linkage. Each repeated identifier declaration inside one source file denotes the same object. Second, external linkage. Each repeated identifier in this entire program denotes the same object. And third, no linkage means that every declaration describes a unique object. Okay, so different scopes. The range of the different scopes is described by the following rules. First, the scope of an identifier which is declared outside the function body extends from the point at which it was declared to the end of the module. The scope of an identifier declared as a function parameter extends from the declaration to the end of the function body. The scope of an identifier declared within the function extends from the declaration to the end of the block in which the declaration occurred. The third rule may be a little surprising. We mentioned some time ago that every block may contain its own declaration, and this is the important aspect of this rule. Consider the sample of code we have shown in the editor. We can see that the scope of the param identifier extends to the entire function body, and the scope of the var identifier extends to the place of the declaration to the end of the function body. And the scope of the I is identifier extends from the place of the declaration to the end of the innermost block, which is here only, and is significantly smaller than the body of the function. So we have the different linkages. Let us assume that our project consists of two modules. First one is the module 1. Here it was declared, here it was written, and then we have the module 2. Okay, here. Okay, so we can say that the param identifier linkage is none. It has a black scope. The fun2 identifier linkage is external, so we use external keyword. The identifier has been declared inside of module 1.c, but after citing the function prototype, it has become available in module 2.c2. Because of the storage class specifier extern, the identifier variable can be defined with external linkage inside or outside translation of module 2.c. Okay, hiding identifiers. We have modified our code a bit. Take a look at it. We have added one declaration inside the innermost block just after the if keyword. Look at the code below. So here we have declared if, and we use the identifier param. Param is greater than 0, and we have declared some expression inside its block. So this is not an error. We have two variables of the same name var, and the scope of the second is fully contained inside the scope of the first. What effect will it have? Sample illustrate a mechanism known as hiding. How does it work? First, the sample illustrates a mechanism known as hiding. Okay, so first, the first declaration of the var variable brings the variable to life, and it thus unknown to the compiler. Second, the next declaration inside the inner block, which is the if here of the variable of the same name hides the previous declaration. This means that the former declaration temporarily loses its meaning and becomes unavailable. And lastly, the second inner variable loses its meaning at the end of the block in which it was declared. At the same time, the first variable regains its accessibility. How about overriding? Let's take a look at the code in the editor. So here we have written the code once again using the different colors for different instances of var variable. So in the first instance, we have declared that var is equals to 2. In the second var, don't have any substitutional value. Okay, so that is the scope of the both variables, which is 2 is only here outside the if parameter, right? So let's have the next slide. So three storage classes. Each of the keywords shown in the figure designate the storage class, a detailed instruction for the compiler saying how to allocate and manipulate the memory. Some of the keywords may precede variable declarations, and like the extern keyword, which we are already familiar with. Some of them may also precede function declaration, and in that case, their meaning may be different. We will now discuss the use of these keywords in some different contexts. So here we have the extern, static, and register. So these are the three storage classes. Okay, extern, static, and register. An internal variable declared as an extern. An example of this kind of declaration might be the following statement: extern int and then amount. You're already aware of the meaning of this declaration. A variable declared as a local variable in the module outside any block causes the compiler to assume that a variable with the same name is defined in another module. It also means that other variables declared as extern and with the same name will be treated as a reference to one and the same variable. Take a look in the two modules. So here's the first module. We have used extern, and here is a function named increment. For the module 2, we have declared an integer outside the function, and it is called main. It is main and increment. So here we have two functions. Okay, so the program emits one as its result. Can you explain why? And the program also emits one because the declaration of the increment function in module 2 is implicitly marked as having external linkage. It can be defined someplace else. Okay, let's have a local function variable. A local function variable declared as static. An example of this of declaration might be this statement: static in counter. A variable declared inside a function with a static attribute is a static variable. To distinguish it from the automatic variable, if a variable declaration is preceded by the static specifier, it means that the variable is brought to life, when the program starts, and is destroyed when the program finishes its work. Take, take a look at the simple function in the editor. The I variable is declared without the static attribute, so it's an automatic variable. It will be created every time the function is invoked and destroyed when the function has finished. This means that every time you invoke the fun function, this function, you will get the following invariable text sent to the std out stream. Just like entering fun is I equals to 0 and exiting fun is I is equals to 1. Now take a look at the modified code in the editor. The I variable is a static variable now. Here we add static keyword. You should expect the following result. First, the I variable will be set up once during the program prologue. Second, the variable will be assigned the initial output, the initial value once. Hence, the variable will be able to keep its value between the function's invocation. So this means that the first function invocation will produce the following text. Entering fun, I is equals to 0, and next will be I is equals to 1 because we have an increment here, right? So while the second invocation will produce the following input. So we have entering fun, I is equals to 1 and exiting 1 is equals to 2. And the third will be I is equals to 2 and exiting will be equals to 3. So we have an increment here, right? So that is how it works, static memory. Okay, let's have a local module variable declared as static. The declaration of a static variable whose scope extends to the whole module has an additional meaning. It does not allow the scope of the variable to be extended beyond the parent module. The variable is not going to be accessible in other modules, even with the external specifier. Consider the example in the editor. We have two separate modules. The variable here, the variable from the first module is now static variable. Its scope extends to the module 1 only, and it is not available in other module. This means that the sample program is erroneous. You won't be able to compile it successfully, since the second module is falsely informed that the compiler that the variable is defined with the external linkage inside another module. So the entity or a variable or a function whose coverage is limited to a single module is said to have internal linkage. So the variable identifier has internal linkage. The module has the sole right to use the variable. Alright, so a function is declared as static. If the static attribute precedes the declaration of the function, it means that the function has internal linkage to the parent module. The function scope is limited to the module in which the function's declaration occurs. We often use this for functions which should not be visible to the user of the module. Consider the example in the editor. Our program now consists of 3 modules. The question is, which of the two fun functions is invoked by the main function? So the answer is hopefully obvious, that is fun, right? Is an internal linkage function in the first module, so it is not available anywhere else. Hence, it cannot be invoked from another module. The fun function declared in the second module is not an internal linkage function and is successfully invoked from the main function. Note that removing the static specifier will cause the program to be no longer correct. Okay, so can you explain why? What do you think? Because you know, guys, that the static memory is the um that is its main one of its main function to be if you add the static specifier on your function, of course, it will be always available in any part of the module. Okay, so a variable declared as a register. An example of register variable is given here. So register int then time. As you probably know, Both program code and its data are stored inside a computer's memory. The processor accesses the memory whenever it has to get the next instruction, and when it needs to read or write any data value. However, each processor has its own small, independent memory. It is coupled with the rest of the CPU inside the same chip and allows the data to be transferred several times faster than from or to the conventional memory. These integrated memory areas are divided between the processor registers. The number of registers is very limited. They are used to perform arithmetic and logical operations, for the temporary storage of intermediate results, and for manipulating the pointers. Normally, the developer is not even aware of the use of the processor registers because the compiler decides independently how to manage them. Sometimes, however, the developer may want to let the compiler know that some of the variables are used intensively and therefore should not be stored in the conventional memory, but instead in registers. In some cases, it may cause the program to execute faster. Despite its advantages, declaring a variable as a register has its limits. Here are some of the restrictions. First, a specifier compiler may refuse to treat a variable as a register if its size exceeds a specific number of bits. The reason is that should the processor use 64-bit registers, there is no physical possibility of storing a large array in there. Second, a compiler may accept only the first few register variable declarations and may silently ignore all subsequent declarations. This is because the number of register is limited and not all of them can be freely used. And third, a variable declared as a register cannot be used as an argument to the unary AND operator. This is a simple consequences of the fact that there is such a variable has no address. So it is shown that the register memory is only limited, right? So it is explained in the first one and the second one. So has its limits. Okay, so a variable declared as a register. Let's take a look at our good old friend, which is the strlen function that accounts the length of the variable or the string. Okay, so here's the example code in the editor. We have strlen2 char, and then we have str pointer, and we have declared here a variable len that is equal to 0 and pointer which is ptr to the str assigned to str, and then we have a while loop here which is increment of the pointer and len increment, and then from then we are going to return the len function. A careful analysis of the code leads us to the conclusion that the len and ptr variables are used very intensively. We can try to improve the performance of the code by declaring them as registers. Look at the modified code in the editor. So here in the editor, you can see that the str, we have declared function here. It is strlent, and we have declared also str pointer character. So this concludes that the len and the ptr variables are already very incentive, uh, very intensive. And as you prove, because we are declaring the register storage, right? The memory. So adding register can improve the performance of our code. So this type of memory is a little bit is good. It can improve the performance of our code that we have written. So guys, all right, so I think yes, this concludes the seventh session, part one of the diverse node mobility front end development program, and we are going to continue it the last part, in the seventh session, part two, and that would be the end of this book. So guys, have a good day, and thank you very much.